Hello, I'm David Debot and I will present our paper Interpretable Concept-Based Memory Reasoning. A promising direction with an explainable AI consists of making models that are explainable by design, such as concept bottleneck models. In these models, one typically uses neural networks to first predict some human understandable concepts from the input. For example, identifying whether an object is yellow, round, and in a bowl. And then these models use these concepts to predict some downstream task, like predicting whether this object is a banana or not. However, there are two problems with this approach. First, the concepts form an accuracy bottleneck, since the downstream prediction relies solely on the concepts and doesn't use any other information that can be found in the input. And second, the human cannot really interpret how these concepts are exactly used in the prediction process, since this final step still involves using a neural network, which is a black box model. To address these issues, we have developed a new concept-based neurosymbolic model called CMR. In addition to predicting concepts, CMR also generates a logic rule. For example, in this figure, yellow and not round implies a banana. Because this generation depends on the entire input and not just on the concepts, this allows CMR to be very accurate in practice. And then, instead of using some black box process for the downstream task, we simply evaluate the rule using the predicted concepts. And this provides interpretability to the human, as the logic rule transparently shows how each concept individually contributes to this specific prediction. The rule generation consists of two components: a set of learned rules that is stored in a memory, and a neural network that acts as a selection mechanism over these rules. For a given input, CMR will choose one of the rules from the memory using this neural network and subsequently evaluate this rule using the concepts that were predicted earlier. Because the rules are transparently stored in the memory, the human can inspect all possible rules that the model might apply. And this, of course, provides some sense of interpretability. And because of the selection mechanism, CMR can use different rules for different examples, making it a very accurate model in practice. In fact, we show that CMR obtains state-of-the-art accuracy near that of black box neural networks on many benchmarks, and we also compare against multiple concept-based competitors, namely multiple different concept bottleneck models and the state-of-the-art concept embedding models and deep concept reasoners. Each time we can show that CMR obtains a comparable or higher level of accuracy when compared to these approaches. We also proved theoretically that CMR is a universal binary classifier regardless of which concepts are used in its architecture. And it is this key property that allows it to obtain a high accuracy even when using very few concepts in practice. When you normally decrease the number of concepts in concept bottleneck models, their downstream task accuracy significantly declines, like you can see in this figure, while CMR's accuracy stays very close to that of a black box model. As mentioned earlier, CMR learns rules transparently in its memory, and this provides some kind of global interpretability to the human, as all possible decision rules are visible regardless of the specific input. This transparency also allows the human to use verification tools to provably verify whether the learned model satisfies some properties of interest. For example, we can verify that whenever the concept bald is predicted to be true, the task wavy hair is predicted to be false. And this is useful for checking, for example, semantic consistency, like in this case, or for checking safety constraints. In conclusion, CMR can be used to create interpretable, verifiable models that achieve near black box accuracy by doing end-to-end rule-based learning. Next time you need a deep learning model, don't use a black box, but use CMR. It's provably accurate and you'll understand what's happening inside. Thank you for your attention.